All right, next up we have Meng Li from Rice, and he's going to be talking about some very interesting work related to image compression, I believe, for different modalities of imaging. And I will let him take it away.
All right, yeah. Thank you, Roy, for the introduction, and also thanks for organizer to have this wonderful session about data science, machine learning, and image stuff. Yeah, so I'm Meng Li. I'm assistant professor at Rice in the Department of Statistics, and my research is about image processing, Bayesian inference stuff. So today, I'm going to talk about image and video compression, and we have a method which can achieve in-situ compression. So this is a joint work with Rongjie Liu, which is a wonderful PhD student of mine, and we are joined Florida State as a tenure track assistant professor, and Lima, a Duke colleague. Okay, all right. So why we do compression? So as like mentioned by some speakers, like from previous sessions, and also from your daily life, you know, the new routine nowadays in science and the industry is we tend to collect massive amounts of high resolution images and videos, right? That is clearly the case once you have a smartphone and can take high resolution pictures. And especially the case in this COVID situation where we have a lot of teleconferences and everybody is kind of on camera. So we produce a lot of images and videos, okay? So then fast and effective image compression for images and videos become increasingly important because of such need. And other than natural images, like in neural image processing, also the images tend to be large, like functional MRI, you have the functional domain, and in longitudinal study, you have like a sequence of images. So it's not only specified to natural images, but also in a scientific image processing, okay? For videos, the same thing, okay? All right, there are a lot of kind of compression algorithm or like available already, but we kind of formulate some desirable properties in compression methods, okay? And so I list all of them here. The first one is we want to make sure at any given compression rate, you can reconstruct the image at high quality, right? That's like a bottom line check. You want to have a good reconstruction. And also you want to see like some PSNR metric, so you can measure whether it's good or not, or you can like visually check whether some key local features are kept. So this is like a visual comparison, and also comparison using some metric, quantitative metric. So the second property we emphasize is computational scalability. We want to make sure the algorithm is fast, like right on time, right? So you can compress a lot of images, like a lot of them, like in no time, and ideally in parallel. Okay, so this is scalability. Third one is we want to have a method that is applicable for different image and video types. So for example, 2D image, 2D colored image, or 2D grayscale image, and also videos where you have a longitudinal dimension, okay, and also colored videos. So we want to have a method that can generally applicable to all of them. And the first one is progressive transformation, which is particularly important once you load an image on a website, so that you can, as long as you transmit more bits, the image becomes clearer, right? But you allow that progressive transformation. And the last one, ease of tuning, right? So like a common user can use your method without some expertise in tuning your algorithm, okay? All right, like in the current literature, there are kind of two classes of algorithms for compression. The first one is kind of a very standard classic, like JPEG 2000, wavelengths, and MPG4. So those are some industry standard. They are very fast methods, okay? And they are fast, but they do not have adaptivity to image-specific features, right? And on the other hand, there is like a deep learning, so learning-based approach. You can like adaptively learn the image-specific features, have high reconstruction quality. But as you know, deep learning rely on massive numbers of training images. So you need to have a lot of training, okay? And we try to achieve a middle ground between these two. And we propose a method called CARP, so compression through adaptive recursive partitioning, okay? It has some nice things. And let me first introduce the workflow, and then let's talk about what it can offer. Given any m-dimensional image, so any m-dimensional, 2D, 3D, colored, or even 4D, right? So depending on whether you have an application for that. And then we do adaptive recursive partitioning with pruning so that we can very aggressively reduce the dimension from m to 1. So at the end of the day, you have a 1D long vector to work with. And then you can apply encoder to have your compressed images, right? So the tricky part is how you come up with that dimension reduction and whether it works well in practice. And then you can go through the other like direction, applying decoder and reconstruction. So you can reconstruct the m-dimensional image. The key parts are in the two black boxes, like how you compress the data using ARP, adaptive recursive partitioning, and then how you do reconstruction. So those are the two key technical challenges in this work. All right. And also here, I want to highlight some kind of modeling perspective in this framework. So CARP uses an optimal permutation of image pixels to reduce its dimension. So at the end of the day, you can reduce m-dimensional image to 1D, right? It's kind of very aggressive. So it will be very interesting to see how it works in practice. And then we use a Bayesian model to infer the best optimal permutation, which is recursive partitioning. So it's like using based on posterior distribution, is adaptive to your data. It's not like predefined. The third point is we use a Bayesian hierarchical model to achieve self-tuning and regularization. So you avoid overfitting. At the same time, you don't need to tune much. And actually, in this method, you just need to specify the compression ratio. Like just one tuning parameter will do. Okay. All right. So then let's say what CARP can offer. So basically, we achieve all these 5 properties. And let's say the first one, reconstruction quality. So using PSNR and a multi-scale similarity index, which are 2 popular metrics in compression community and also image community in general. So we can see CARP achieves the state-of-art performance. So we really compare CARP with a lot of other approaches, including deep learning. And in terms of these 2 metrics, we are almost uniformly the best. Okay. Second one is computational scalability. So CARP is linearly scalable. Basically, it's linear in terms of the number of pixels you have in the image. Okay, so linear. And the third one is applicable to any m-dimensional image. Okay, and the first one is because we are using wavelet, so we enjoy progressive transformation property. So in this kind of small toy example from left to right, if you transmit like more bits, then the image becomes clear. So this is just a natural property of wavelets. The last one is easy with tuning. We just have one single parameter so that we can achieve in-situ compression without relying on any training data set. Okay. All right. So let's see some numerical example first. We are going to use 3 data sets to demonstrate the performance of CARP. The first is 2D still images. This is from a kind of challenging image compression. And they are colored images. They are from real life images. And the second data set is YouTube videos. So there is a YouTube video data set, and which is kind of benchmark data set. We just keep using this one because people use this one for comparison. And the last one is a video on a parking lot. So and as you can imagine, it's very different from real life video. But we want to test the performance of CARP using a variety of scenarios reflected by these 3 data sets. Okay, they are all true images. We do not do simulation in compression. Okay. All right. Let's first see the average performance. We check PSNR. There are 3 plots corresponding to 3 data sets. From left to right, they are for the 2D still images, YouTube video, and the parking lot video. Okay. And let's randomly pick one of them. Maybe the first one from the very left 2D still image data set. We compare CARP with JPEG, JPEG 2000, E2E deep learning, and BPG. So BPG and JPEG, they are kind of industry standard. And you see the blue curve stay on the top. So that means on average, CARP is the best among all these choices. And for the second data set, CARP, we compare CARP because it's video. So we kind of try MPG4 and HEVC for this data set because they are videos. And CARP is among the best, not the best on average. So HEVC is the best if you talk about PSNR. And for the third data set, CARP is apparently the best. So the margin is quite significant between CARP and the other approaches. Okay, so let's look at the second one, the one on the middle. And HEVC is the best, right? But PSNR is not everything. Yeah, PSNR is a global metric. So some people actually propose like a multi-scale similarity index to measure the reconstruction quality, which is widely viewed as probably better to PSNR, but we do not kind of make a very careful comparison and claim on that. So we compare both. And the next picture give you multi-scale similarity index, and the larger the better. Is from 0 to 1, so it's well calibrated. Let's look at the one in the middle. So the blue curve, which is CARP, is clearly the best now. So if you change metric, actually the comparison becomes different. But no matter which metric you use, similarity index or PSNR, CARP is one of the best. Actually, in this 6+, CARP is universally the best in 5 of them. And for the comparison of HEVC, they are kind of close to each other. Okay, so this is an average performance comparison. So let's look at some individual image, because in each data set, we have many images. So maybe it's useful to look at individual image. And here on the right panel, there are some comparison by dividing the PSNR with the PSNR of CARP. So for all those individual images, okay? And if you see all those curves are below 1, then that means CARP is uniformly the best. Okay, so let's see the comparison. Actually, for nearly all images we test on, CARP is almost the best, right? So maybe we lose to JPEG 2000 in 2 data, in 2 images, but yeah, not much, right? As you can see, most of them are stay below 1. So on almost all images, CARP is uniformly the best. Okay, and also it's useful to compare some like visual details. And here we have this like the original figure in A. When compression ratio is 45, you can see CARP reconstructs the image quite sharply. So especially you see the small breaks and the boundary is very sharp. So the contrast is maintained, which is some appealing property in our opinions. Okay, and of course you can check some other constructions. And I want to pick like E2E deep learning. So this one does not have good performance in this particular data set. We need to acknowledge that maybe with a better training, deep learning can be better. But for this data set, this is not what we observe. Okay, and also for the 3D data set and CARP, and you can see the top left corner. So CARP approach has some very good PSNR, peak signal to noise ratio. When the compression ratio is almost 300, we can still maintain 50 PSNR, right? Which is truly amazing. So the reason is for parking lot data set, from frame to frame, the images do not change much. And CARP is particularly useful for those kind of small local change, because if it does not change much, and CARP can detect that and use one single point to summarize everything. Yeah. And in this comparison, CARP is uniformly the best compared to HEVC, JPEG, MPG4, JPEG 2000, and BPG. Okay. All right. And some detailed visualization and well, which is kind of subjective. So we probably should rely on the quantitative comparison for different methods. But if you look at some details, CARP can recover the original image fairly well compared to alternatives. Okay. All right. So then let's better talk about some model. So why it works. Actually, CARP decomposes the entire images into the spatial structure and 1D intensity. So the spatial structure is done by recursive dialectic partitioning in a Bayesian framework. And given that partition, we have a Bayesian wavelet regression framework given by formula 1 to 5, and there are some more math here. So I want to make this talk not that technical, but if you want to talk more, we can certainly have that conversation. And at the end of the day, we have a dynamic programming to learn the best of representation. Okay. All right. So summary. We proposed this CARP approach and works pretty well, and achieve state-of-the-art compression performance. And this is a reference published in CVPR earlier this year, and we have software available. And if you and also license the software if there is some industry friends have interest in this one. All right, Q&A. Thank you.
Thank you very much, Meng. That was very interesting, and the results look very impressive. We have one question. I think you partially answered this, but I'll read the full question. Do you have any tests on very sharp transitions or even anomaly preservation tests when you have one non-zero pixel which is preserved during multiple compression levels? And then the comment says this is critical for scientific applications.
This is a wonderful question. Yeah, indeed, we have thought about this, and we have some kind of idea along this line, but we haven't done some kind of concrete work because we do not have like some killer application for this type of a scenario. But indeed, it's very possible. And actually, CARP should be good at this because CARP is using a multi-scale framework. So if there is some local pixel that show some extreme change instead of the global background, we should be able to kind of focus on that area fairly quickly. So we are very confident in the performance of CARP in that particular scenario. So I think this is a great question and a great direction to look into in the future.
All right, thank you very much. We're out of time for this session, so I'd like to thank all the speakers again. For the attendees, please stick around and head over to our virtual networking session right now that's being sponsored by our conference sponsors. So enjoy that, and I think we have another more networking after that, and we'll see everyone, I think, tomorrow, if I have the schedule correct. All right, thank you.